Hello, everyone. Good morning. It's another lovely Tuesday. I hope we're having a lovely day. I hope you are enjoying your day, and I hope your week has been going well. Okay, so today we're going to be having physics as usual. You know, that's what we're doing today. But let's look at some fun facts that I just want to share with you today. Okay, so look at some fun facts in physics and let's see what you know about this person. Okay, so I'm going to show you a picture now, and I want you to try to tell me who the person is. So, who is this man? You can figure it out. You know, that means you actually have already seen this picture before. Well, who is this man? You can try to guess. Guessing is allowed. Guessing is allowed. So try to guess. Try to guess who he is. Okay, let me give you a hint. Eureka! Eureka, that's the hint. Okay, so if you know that statement, you know that this person is actually Archimedes. Archimedes of Syracuse. I like that. I like that name. Okay, so his name is actually Archimedes, and he's famous because of that expression, Eureka, meaning I have found it. Okay, so actually, we're just going to be looking at some of, not everything, but we're just going to check some of his, works and how did he contribute to our daily life that we live now? How was he helpful, to us? How has his inventions been helpful to us now? So let's look at one out of the two we're just going to look at today. Okay, so I don't know if you've heard of the Archimedes principle before, but I know that if you haven't, you can just try to follow. But I think it's a common. It's actually a topic on its own, and we'll probably still go into that another time. But you know, Archimedes principle, and that's one of the major things actually that he's known for. So what is this principle all about? Actually, his principle, the summary of this principle is that if a solid body actually falls into a liquid, it displaces its volume. The volume of liquid that it displaces is the same thing as its own volume. Okay, that's just a summary of the principle. As time goes on, when we get into the principle another time, we'll look at the definition and all its angles. Okay, so what the principle states is that if a body falls into a liquid, it displaces a volume of liquid that is equal to its volume, and it experiences an upthrust and so on and so forth. And it's a long thing. But now, what is the application of this principle? Now, have you ever seen a sheep up close? I don't know if you've seen one up close, but even if you've not seen one up close, you've seen some in movies. Yeah, you've seen some in movies. Look at a picture of a sheep there. Have you ever thought to yourself, why doesn't this sheep sink? Why doesn't the ship sink? Because most times if you put an object into an ocean, it goes down if it has any weight at all, except it's a balloon or something. It goes down into the ocean, okay, and you don't see it anymore. So Archimedes' principle is actually taking into account when making ships. Okay, so you can see without Archimedes' principle, you probably, you probably enter into a ship, or there won't even be ships because it would be like a dangerous thing to go on the ocean. So you can see that it was actually helpful to have Archimedes' principle, to have the knowledge of Archimedes' principle. So that's a good one from Archimedes. Let's check out something else. Okay, let's check out something else. So what else did he do? What else did Archimedes do for us, help us with? Now, I think you know what this symbol is. Have you ever seen this symbol before? Okay, well, if you haven't, I know you have, but this is actually pi. This is pi, and it's one of the most important, should I say organisms? It's not a living thing, so I can't say organism. It's one of the most important values in geometry, right? And guess what? It was Archimedes that actually derived the value of pi. Actually, there has been an estimated value of I think 3.15 something by the Egyptians in those days. But Archimedes used the Hellenistic method of mathematics, and he derived that value of pi. That value that we know as 22 over 7 or 3.141, and then it goes on and on. Pi is a very wonderful number. So Archimedes was actually the person that proved that derived this value. So you should be thanking Archimedes every time you calculate the area of a circle. You should be thanking Archimedes every time you find the volume of a cylinder. You should be thanking Archimedes every time you do anything that has to do with pi, because he was the one that actually derived it for us. So you can see he wasn't just a physicist, he did so many things in mathematics also. So we've looked at his contributions to physics, to math, and to so many other things, okay? But he actually has some more contributions to daily life. You can try to, see them and figure some of them out and research on them. I don't want to tell you more, so just try to find out more. Try to find out more. Okay, so that is Archimedes. He's a lovely person, although I never knew him physically, but the principles that he gave to us are amazing, and we're grateful for them. Okay, so let's get into what we have to do today. We have a long journey ahead of us. Okay, so what do I need you to know today? It's a simple one. What I need you to know are the laws of motion. The laws of motion and their applications. We're not going to look at all. Okay, we're not going to be able to check out everything today, but let's just see how far we can go in today's class. So, Newton's laws of motion. Newton's laws of motion, that's what we're going to be looking at today. So let's take a quick review. Can you define motion? We talked about equations of motion in the last class, and then we defined motion. So motion is the visible movement of an object from one position to another. It can be defined in many ways anyway, but that's one of the definitions of motion. So remember, we talked about people in motion, a body in motion, a boy in motion, a girl in motion, and all that. We also talked about the types of motion, so can you mention them? Try to say them to yourself if you can mention them. Okay, so you should have said something like translational motion, circular motion, random motion, rotational motion, oscillatory motion, and so on and so forth. So those are the types of motion we also discussed in our last class. Okay, so let's go to the laws now. Let's talk about law 1. That's the first law of Newton's first law of motion. Now, what does Newton's first law of motion state? Okay, we're going to get into that. But before we can even talk about the first law of motion, we need to understand a concept called inertia. Now, what is inertia? The inertia of a body is its reluctance to remain at rest, or its reluctance to be brought to rest if it is in motion on a straight line. Okay, so inertia simply has to do with, okay, body is at rest. Okay, it has a phenomenon where it exhibits a reluctance to remain at rest, and its reluctance to be brought to rest if it is, already in motion. Okay, so now that brings us down to the law of inertia. That's Newton's first law of motion, is also called the law of inertia. Now, what does this law state? It states that everybody, no matter what the body is, it can be anything. It can be a person, it can be a non-living object. Every single body will continue in its state of rest or of uniform motion in a straight line, unless it is compelled to change that state by an external force. So everybody that is at rest will remain at rest, and everybody that is in motion in uniform motion will remain in uniform motion in a straight line, except it is acted upon by an external force. That's what Newton's first law, states. I'll show you, an example of that now. So, for example, we have two balls here. The one on the left is a ball in motion. Probably it was kicked, and then it's in motion. Now, what Newton's law says is that if this ball is in motion, in uniform motion, it will continue to be in uniform motion. Uniform motion, talking about uniform motion. It continues to be in uniform motion except an external force acts in it. And then the second ball that's on the right is at rest. Newton's law, first law, says that that ball will continue to be at rest except an external force acts in it. So that's the concept of Newton's first law. So let's talk about the application of Newton's first law of motion. Now, have you ever thought about the fact that whenever you leave something somewhere, you meet it right where you left it, right? You drop a book on the table and you meet that book right on the table where you left it, except someone, moves that book, you leave it right where you left it. That's an example of, the application of Newton's first law. Now, another very, 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 very important one is the need for seatbelts. Is the need for seatbelts. Now, why is it that you need a seatbelt when you're driving? Now, because, for example, if you are forced to stop abruptly, inertia, concept of inertia, still makes it in such a way that there is a forward lurch when you're forced to stop abruptly. Okay. Now, if you're not wearing a seatbelt, you could fly through the window. I'm sorry, the screen. You could fly through. You could fly through, and that's not a good thing. So it's not something we want. So that's the reason why you're asked to, use your seatbelt when driving and all that. So you can see that this is also an application of Newton's first law. If we didn't know about Newton's first law, we probably wouldn't have thought to the direction of using seatbelts. So that's another good one from the first law of motion. So let's go to the second law quickly. Before we do any calculations, let's just analyze all the laws. So the second law of motion now, Newton's second law of motion. Before we can even go to Newton's second law of motion, we need to talk about momentum, okay? Because momentum is a key factor in the second law of motion. Momentum is a key factor. Now, what is momentum? Momentum is defined as the product of a body's mass and its velocity. It's as easy as that. It's the product of the body, mass of the body, and the velocity of that body. Now, mathematically, we can say that momentum, capital letter M now, is mass times velocity, okay, mv. So mv. Now, what does the second law state now? The second law of motion states that the rate of change of momentum, of a body is proportional to the external force that's applied to that body, and then it takes place in the direction of the force. So the rate of change of, we talked about momentum, right? We talked about momentum as being mass times velocity. Now the rate at which momentum is changing, the rate at which the momentum of the body changes, that's momentum with time, is proportional to the force that acts on that body. It's proportional to an external force that's acting on that body, and it takes place in the direction of the force. Okay, so let's express this mathematically so that you can understand what I'm saying. Now, but before that, momentum, change in momentum, let's look at what change in momentum is. Of course, change in momentum is momentum, the momentum, mv minus mu over t. That's the rate of change of momentum. Change in momentum is mv minus mu, so rate of change of momentum should be mv minus mu over t. Okay, that's the rate of change of momentum. Now, we want to express Newton's second law. Newton's second law states that the rate of change of momentum mv minus mu over t is proportional to the force, right? So we can say F is proportional to mv minus mu over t. Now, we introduce a constant. In mathematics, if we want to get rid of the proportionality sign, we need to introduce a constant. So F equals to K times mv minus mu over t. Okay? Now, we can make some manipulations, factorize m out of that equation, of that expression. So we have F equals to K into m v minus u over t. Okay? So remember that this can be expressed now as Km. Bring out the m that has been brought out from the brackets, that has been brought out from the expression rather, and we say Km into v minus u over t. But then v minus u over t rings a bell, doesn't it? We talked about the equations of motion, so v minus u over t should ring a bell. V minus u over t is actually acceleration. So v minus u over t is a. So a is v minus u over t, so we can remove v minus u over t and say that F equals to K M A. Now, but there's a problem, not a problem. I don't know why I like saying there's a problem. There's no problem. There's just something else we need to resolve. So K is the constant, right? Okay, so now let's talk about 1 unit of force. Let's talk about 1 unit of force, 1 kg of a body, 1 unit of acceleration. Then K will be 1 in that case, right? K will be 1. So in that case, we can say simply that F is ma. Okay? That F is ma. And the unit of force is newtons. So N, newtons. Okay? So step all step by step, and you'll be able to see how, Newton's second law of motion was actually derived. And then it gives us F equals ma. Okay? All right. So we're still on the second law, but I want us to talk about the phenomenon called impulse. I don't know if you've heard of impulse, that the word impulse. I did it on impulse. Or it was an impulsive decision. I wasn't, I didn't have enough time to think, so I just made an impulsive decision. I don't know if you've heard that in English language, so you have an idea that impulse um, means acting suddenly or acting without prior thoughts about that phenomenon or thing that you're trying to work on. Now, let's now talk about the meaning of impulse in physics. Now, the impulse of a force is the instantaneous response of an object to the force that acts on it. Okay, so a force acts on an object, and that object responds instantaneously to that force. That's what we call impulse in physics. It's very similar to making an impulsive decision. Something out of the blue, something sudden. Okay? So that's the meaning of impulse in physics. Now, it's in mathematics, mathematically, it can be said to be the product of, the force applied and the time taken to bring about the change in the momentum of that object. So it can be expressed as, force times time. The force applied times the time taken to bring that change in momentum bring that change in momentum to come to pass. Let's say to pass. So impulse is force times time, which is ft, and the unit is Newton seconds, ns, Newton seconds. Okay, take note of all these things. Okay, now impulse is also change in momentum. Impulse is also equal to change in momentum. So that simply means that impulse is mv minus mu. Now, if we compare those two statements, we said impulse is ft, and we said impulse is mv minus mu, so automatically ft is mv minus mu also. Okay, so we're just doing a little mathematics here. ft equals mv minus mu also. So just take note of all these formulas in case you're given something that is, specified in this direction, so you can use either of these formulas to find that value. For example, if you're asked to find the impulse of a body and you're given the force and the time, you know which formula to use. If you're asked to find the impulse of a body, you're given the mass and the velocities, you know what to do. And let's assume you're not given the impulse, you're given the force and the time, and you're given the velocities and asked to find mass, for example, then you know that you need to use Ft equals mv minus mg. So that's just the gist of everything. So try to, know the formulas and know when to use them, know when it's applicable. Okay? So let's talk about applications of Newton's second law now. Let's talk about applications of Newton's second law. Now, remember that Newton's second law states that, based on our proof, F is equal to ma. So the force in that case is proportional to the mass, right? We came down to proving it, solving it, resolving, and then we got F equals ma. So in essence, the force is proportional to the mass of the body. The force that will be applied on the body is proportional to the mass of the body. So let me show you an example of application of the law. Now, which of these cards will be more difficult to push? Think about it. Which of these cards will be more difficult to push? Is it the one on the left or the one on the right? Is it the one that's empty or the one that's full? So let me give you a second to think about that. Which of these cards will be more difficult to push? Okay, let's see. The answer is the one on the right. That's the one that is full. Why? Because it has more mass. So automatically the force required for the card with more mass is also higher. Do you get the concept? The one that's empty will require less force than the one that's full, because we already stated that the force is proportional to the mass. So this is an application of Newton's second law, or something you can see in daily life. You go to the mat, you know that when you're pushing an empty cart, it's just easy. You just push it so easily, But when you have a cart that has a lot, when you're buying a lot of things for Christmas or New Year's, and it becomes more difficult to push. So that's a simple, easy to remember application of the second law. So let's take our examples now. Let's take some examples, on how to, apply these laws. Number one, I'm just going to give you some easy examples. Calculate the force that will exert an acceleration of 20 meters per second to a mass of 4 kg. So we have an object that is whose mass is 4 kg. We want this object to move at an acceleration of 20 meters per second square, but we want to know the force we need to apply to this object to make it move, for example, you know. So let's take our solution. So we have A as 20 meters per second square and M as 4 kg, and we're to find F. But remember that F is MA. From our formula that was derived, F is equal to MA. So we can say that F is 4 times 20, and that gives us 80 newtons. 80 newtons, okay? Number two, a body of mass 100 kg at rest is pushed to a distance of 20 meters by a force of 90 newtons. Calculate the time taken to cover the distance. This one is a little more, complicated than the first one, but that's also simple. So let's just break it down and see how to do it. So let's write out the parameters. We have mass is 100 kg, the distance, okay, it's at rest, of course, so the speed, initial velocity is 0 meters per second. The distance covered is 20 meters. The force applied is 90 newtons, and we are to calculate the time taken to cover that distance. Fine, we have to find the time. I see that, but we need to find something that might be easier first, or something that will take us where we need to go. So we have force and mass. Remember that F is MA, right? Since we have F and M, okay, let's try to get A first. So F is MA. Now that means 90 is equal to 100 times A. So A will be 90 over 100, which is 9 over 10 meters per second square. So now that we've been able to get our acceleration, we now need to find our time. Okay, now what we need to do is to go back to our equations of motion, which we discussed in the last class. So we're going to now, we need to now know which equation we're going to use. So if we analyze our equations, we'll see that we can actually use this equation. S equals to UT plus half AT squared. Now we're looking for T, so let's substitute every other thing. So S is 20, U is 0, so UT goes away and becomes 0, plus half times A, which is 9 over 10, times T squared, which we're looking for. So this becomes 20 equals to 9 over 20 T squared. If we cross multiply here, we'd get something like T squared equals 400 over 9. T squared equals 400 over 9. Okay, so T will be square root of 400 over 9, which will give us 20 over 3, and that will give us T as 6.7 seconds. So it will take us 6.7 seconds to push that body of mass 100 kg from rest to a distance of 20 meters with an applied force of 90 newtons. Okay, so that's that for example 2. Let's now talk about the weight of a body in a lift. So this is another application of Newton's law. So let's look at the weight of a body in a lift now. Now, this is a lift. This is a picture of a lift, right? This is a picture of a lift. Now, in this lift, a body can actually be, a person can just be standing, not moving. A person can be moving up in a lift, or a person can be moving down in a lift. So we're going to be looking at different cases of a person in that lift. So for case 1, what a scenario where the lift is not moving, the lift is at rest. What happens then? Of course, the weight of that body, of the weight of a person in the lift is simply mg. That's mass times the acceleration due to gravity, which is the usual value for the weight of the body. The weight there is just going to be mg. Now, but what about case 2, where this man is in the lift and he has a weight his weight is acting downwards and the reaction of the lift is acting upwards, and then the lift is ascending or it could be descending, but is moving with uniform velocity. So there's no acceleration. It's moving with uniform velocity. What is the weight, apparent weight of this man? How does the man feel in the lift? What's the weight of the man? Now, first of all, you need to know that the reaction minus the weight is actually the mass times acceleration, MA. Now, but we already know that the lift is not accelerating, okay? So R minus W is going to be 0 since MA is 0. So if R minus W is 0, then R equals to W. So that simply means that the reaction of the body, of the weight of the lift, sorry, is equal to the weight of the man. So automatically the weight of the man is, mg still. The apparent weight of the man still remains mg. Now, but case 3 now, still have the same parameters, the weight of the man acting down as a reaction of the lift. Now, the case 3 now is when the lift is accelerating now. The lift is accelerating upwards. What's the apparent weight of this man? How does he feel? Actually, the man feels heavier. He feels heavier because his total weight is not just mg, but also ma. So also the acceleration of the lift comes into play now. So the apparent weight of the man is mg plus ma. Now case 4, still the same parameters. When the lift descends, it's going down, the lift is going down and it's accelerating. So when the acceleration is great and less than the acceleration due to gravity, we can say that the weight is mg, apparent weight of the man is less, is mg minus ma. But when the acceleration of the lift is greater than the acceleration due to gravity, we say that the apparent weight of the man is ma minus mg. Okay, so these are just some things that you need to know about, the body moving, a body in a lift that is moving either upwards or downwards, whether with a velocity, uniform velocity, or with an acceleration. Okay, so just take note of all these things. Now, I want to ask you this question: what about a scenario where the lift just falls freely? The lift is falling freely. There's no, you cannot pinpoint a velocity, uniform velocity, or an acceleration. The lift is just falling. What happens to the body? How does the man feel? What is his apparent weight when the lift falls freely? Think about it, think about it, think about it. When the lift falls freely, what's the apparent weight of this man? Okay, let me tell you. His apparent weight is nothing. He's weightless. He feels weightless. He's weightless when the body and the lift falls freely, or the elevator falls freely. Okay? So the man is actually weightless. Now let's take an example. We still have that same man. That same man in the lift now, but we have some parameters attached to it. So a man of mass 50 kg ascends a building in a lift moving at 2 meters per second square. That's the acceleration. What should be the scale reading as he approaches his destination? So what is his apparent weight in essence? What is his apparent weight? We've already said previously though that the apparent weight of a body that's ascending in a lift is mg plus ma, or m into g plus a. So we're just going to find that now. So that's going to be 50 kg into 10. Of course, when you're not giving acceleration due to gravity g, you can use 9.8, but let's just use 10 here. So 10 plus 2, that gives us 50 times 12, and that gives us 600 newtons. So the apparent weight of this man is 600 newtons. Okay, so let's take a quick summary of everything. We talked about the first law and the second law. We still have the third law to go. We won't be doing that today anyway, but in our next class. So we talked about the first law, which is the law of inertia, and then inertia is the reluctance of a body to be brought to rest or to remain at rest, depending on the situation at hand. And then we talked about the law of inertia, how everybody will continue moving or continue in its state of rest, except it's acted upon by an external force. Then we moved on to the second law, and we talked about momentum as the product of the mass of the body and its velocity. And we said, the second law is that the applied force is proportional to the, rate of change of momentum of the body, and it takes place in the direction of the force. Then we took some examples, talked about some applications, remember that? And then we talked about the weight of the body in a lift. That's what we just finished discussing. And then we talked about when it's not moving at rest, when it's moving with a uniform velocity, or when it's ascending or descending with an acceleration. So try to take note of everything that has been discussed so that in case you find questions that you need to apply these formulas to, you would be able to apply, or if you're asked to derive any of these formulas, you should be able to derive them. So I want you to try this out. Calculate the force required to move a 30 kg body with an acceleration of 15 meters per second square. And then a man of mass 75 kg descends a skyscraper in an elevator whose acceleration is 5 meters per second square. What is his apparent weight? So these are the answers. If you work them out correctly, you should get this. Work them out correctly. So that should be your answer. Then also I want you to try to visit quizzes.com, and you can just play games of force, momentum, and the likes. Just try to search for some games and play them. But try to solve these questions also. Okay, so that's that for our class today. Of course, we will continue from here in our next class. I hope to see you guys again on Tuesday next week. Remember to subscribe, remember to like the video, leave a comment on what you want us to do, or contributions, questions, and more things you need more explanation on. And don't forget to share to your friends if you feel it will help them, to understand the topic better. So have a lovely day and take care of yourselves. Bye.